Welcome to the deep dive. We're here to take complex info, sort of unpack it, and distill it down into clear, engaging insights for you. Today, we're jumping into a really fascinating and honestly pretty critical area: how well large language models, LLMs, can actually follow instructions. Specifically, we're looking at a brand new study from Distill AI. It's called How Many Instructions Can LLMs Follow at Once? And they've introduced this benchmark, IFScale, which tackles a question that's just become vital for anyone actually using LLMs in the real world. I mean, how well do these models really do when you give them not just one or two things to follow, but dozens, maybe even hundreds, all at the same time? So our mission today is to unpack this research, get a grip on the main findings, and sort of highlight what it all means for how we think about and, importantly, how we use these advanced AI models.
Yeah, and what's really interesting is just how much we've started relying on LLMs, especially in, production systems. Systems where you need them to stick precisely to lots and lots of different rules or specifications. Think about like generating content that needs to follow strict style guides, or maybe factual requirements, or automated workflows that have to follow business rules to the letter. Even those agent systems that need really solid memory. Modern applications, they're asking models to do complex stuff while juggling multiple instructions simultaneously. And we've all seen or heard about the failures, right? Chatbots making up policies or giving bad advice. Those failures really highlight the risks when instruction following isn't quite perfect or maybe even breaks down under pressure.
Right, it almost feels a bit strange because we're seeing these huge leaps in capability elsewhere. Context windows getting massive, millions of tokens, and reasoning seems better too. So you'd think, theoretically, they should be able to handle way more instructions at once. The tech seems like it should be there.
And that brings up a really key question then. If they can process these huge contexts, how many instructions can they actually manage effectively before things start to go wrong, before performance really drops off? Most of the benchmarks we've had usually test models with just one or maybe a handful of instructions, which leaves this big gap in understanding how they cope with high instruction density, exactly what these complex applications need. So this Distill AI study, it's aiming squarely at filling that gap.
Okay, so the old benchmarks weren't really up to the job for this specific question. How did the researchers actually design IFScale? How does it work? How does it test these models?
Well, IFScale is designed pretty cleverly to look specifically at how performance degrades as you add more instructions. The main task they give the LLM is, on the surface, simple: generate a professional business report. But here's the twist. The report has to include a specific list of keywords. Each instruction is just a constraint to include one specific keyword.
Ah, so adding more keywords means adding more instructions. Simple.
Exactly. It makes it really easy to scale the density. They ramped it up from just 10 instructions all the way to 500.
Wow, 500.
Yeah, in steps of 10. And grading performance is automated too. They use this wildcard-enabled regex matching to check if the keywords were included. It's like a smart search that can find the keyword, even if it's slightly varied, which helps make the grading accurate and scalable.
Okay, that sounds thorough. What kind of keywords were they using for this business report task? Were they just random words?
Oh no, they were very specific about that. They put together this list of 500 high-precision, business-relevant single words.
Yeah.
And they didn't just make them up. They pulled them from US SEC 10K filings, those big annual reports companies file.
Right, the detailed financial ones.
Yeah, and then they filtered them, made sure they were standard English, and crucially, ensured they were semantically unique, meaning each keyword really was a distinct instruction, no overlap or ambiguity.
Right.
It keeps the task challenging but fair, kind of mirroring what an LLM might face in a real business context.
Okay, so they put, 20 state-of-the-art models through this IFScale ringer. What was the big takeaway? Did the results surprise you?
Well, the main headline was pretty sobering, actually. Even the absolute best models, the frontier ones, only managed about 68% accuracy when faced with all 500 instructions.
Only 68%. That's quite a drop.
It is. It tells us pretty clearly that you can't expect perfection when you load these models up with lots of constraints. Performance does degrade significantly. But what was really fascinating was how it degraded. It wasn't the same for all models. The study found basically 3 distinct patterns of failure, like different ways they break under pressure.
3 patterns. Okay, what were they?
So first, there's what they called threshold decay. Think of models like Google's Gemini 2.5 Pro and another one called O3. These guys performed almost perfectly, like 95, 100% accuracy, up to a point maybe 150, sometimes 250 instructions.
Okay, holding strong.
Exactly. But once they hit that threshold, bam, performance dropped off sharply. And often it became more variable too, less reliable run to run. These tend to be the reasoning-focused models.
Interesting. What's the second pattern?
That's linear decay. Models like GPT 4.1 and an earlier Claude model, 3.7 Sonnet, show this. Their accuracy just went down steadily and predictably as you added more instructions.
Mm.
No sudden cliff, just a consistent, gradual slide across the whole range.
More predictable, but still declining. And the
The
third?
third is exponential decay.
Mm.
Here, performance drops really fast, right at the beginning, even with just a moderate number of instructions. After that initial steep fall, the accuracy kind of levels off, but at a really low point, maybe only 7% to 15%.
Ouch.
Yeah. Models like GPT-4 and one called Llama 4 Scout showed this pattern. They seem to get overwhelmed very quickly.
That's a huge range of behaviors.
Yeah.
So aside from these patterns, were there any sort of general trends? Like, are newer, bigger models always the winners here? Or was it more complicated?
It's definitely more complicated than just bigger is better. I mean, generally speaking, yes, the reasoning models tended to do better than the general purpose ones.
Mm.
And newer or larger models often outperformed older or smaller ones. That part holds true, mostly.
Mostly. So there were exceptions.
Oh yeah, some really interesting ones. Take Grok 3 from XAI. It performed almost as well as O3, that top reasoning model, even though it wasn't run in its reasoning mode for these tests.
Huh.
And maybe even more surprising, Claude 3.7 Sonnet. Remember, that's an earlier mol. Claude model actually did better than newer ones like Opus 4 and Sonnet 4 when maxed out at 500 instructions.
Really? Why would that be?
The study doesn't definitively say why, but it shows performance isn't always a straight line forward with new versions. And maybe the biggest surprise was GPT-4.
What about it?
It showed pretty weak performance overall, that rapid exponential decay we talked about. Much more like a smaller model, not what you might expect from a cutting-edge release.
So size and release date aren't the whole story when it comes to handling lots of instructions.
Not at all. It suggests the internal architecture or training focus really matters for this specific capability.
Okay, so accuracy drops, and it drops in different ways. What about consistency? Reliability. Did the models become more erratic as the pressure increased? Because that's crucial for real-world use, right?
Absolutely crucial. And they did look at variance across different runs. Again, they found roughly 3 types of behavior. The top performers, like Gemini 2.5 Pro, O3, Grok 3 Beta, their variance actually increased steadily as instructions went up.
Increased, so they got less reliable even if their average was higher.
Kind of, yeah. Less predictable from one run to the next. Then you had the mid-tier models like Gemini 2.5 Flash, Claude Sonnet 4. They had this weird peak in variance somewhere in the middle, around 150 to 300 instructions, like an unstable zone where they really struggled and became erratic.
A shaky middle ground.
Right. And then the worst performers, the ones that failed quickly, their variance actually went down almost immediately.
Down? How does that work?
It sounds odd, but it suggests they just collapsed so completely under the load that they started failing in a very consistent, uniform way. They became predictably bad, you could say.
Ah, okay. Consistent failure.
Exactly. Though there was one big outlier, Llama 4 Maverick, which was just highly variable across the board. Maybe something different going on internally there.
Fascinating. What about the order of instructions? We humans tend to remember the first things on a list better. Do LLMs show a similar bias?
They do. That's what the study calls primacy effects, doing better on instructions that appear earlier in the prompt. And they found a really consistent pattern across almost all the models.
Okay, what was the pattern?
Well, at low instruction counts, the effect is minimal because the models can handle everything pretty well. But the primacy effect, that bias towards the beginning, it peaks right around 150 to 200 instructions.
Right in that zone where models start to struggle.
Exactly. It's like that's when they start having to prioritize, consciously or not, and they fall back on remembering the first things they were told. But here's another twist. When you get to really extreme densities, like over 300 instructions, that primacy effect actually levels off or even decreases. The ratios comparing first half to second half accuracy get closer to 1.0 or 1.5.
So the bias fades when they're totally overloaded.
It seems so. It suggests a shift. It's no longer about selectively following the early instructions. It's more like uniform failure across the board. They hit an instruction saturation point. And that means just putting important stuff at the start of your prompt might not help much once the model is truly swamped.
That has big implications for how we write prompts for complex tasks. So when they do fail an instruction, what kind of mistake are they making? Are they just leaving the keyword out, or are they maybe putting in a similar word?
Good question. The study looked at exactly that, breaking errors into 2 types. Omission errors, the keyword is just completely missing.
Hmm.
And modification errors where they include a variation like running instead of run.
Okay.
And the finding was overwhelming. As instruction density goes up, models massively default to omission errors. They just leave the word out.
They'd rather say nothing than get it slightly wrong.
It seems that way for most models. At 500 instructions, some models like Llama 4 Scout had omission errors happening over 30 times more often than modification errors.
30 times.
Yeah. Llama 4 Maverick, Claude 3.5 Haiku, Llama 4 Scout, they all showed this strong bias towards just omitting things. But, interestingly, the reasoning models, O3 and O4 Mini, had lower ratios. They were more likely to try a modification rather than just drop the instruction entirely when under pressure.
So they attempt to satisfy it, even if imperfectly.
Seems like it. And Gemini 2.5 Pro was notable because its ratio actually decreased as density went up, meaning it became more likely to try modifications under heavy load, which is quite impressive.
Okay, we've talked accuracy, variance, error types. What about efficiency? Balancing performance with, how long it takes, the compute cost.
Right. Efficiency defined here as accuracy divided by latency, or
Yeah.
how long it took. And the trend was universal.
Mm-hmm.
Efficiency goes down for all models as instructions increase. They all get slower relative to how many instructions they get right, converging towards low efficiency at high densities.
Makes sense. Any standouts?
Well, the reasoning models really showed the biggest latency increases. They got dramatically slower under load. O4 Mini was the extreme example. It went from about 12 seconds for 10 instructions up to over 430 seconds. That's over 7 minutes for 250 instructions.
Oh.
Yeah, huge slowdown. On the flip side, the fast, often smaller models like Grok 3 Mini and Gemini 2.5 Flash actually had the best efficiency ratios overall. It shows that speed can sometimes make up for slightly lower accuracy, depending on what you need.
So a trade-off between raw accuracy and speed-adjusted efficiency.
Exactly. Though Grok 3, the larger one, also did well here, managing both good accuracy and good efficiency. A strong combination.
Okay, one last crucial piece. Following instructions is one thing, but did asking them to follow hundreds of keyword instructions mess up the main task, actually writing a coherent business report? Did the reports turn into gibberish?
That's a really important point. And for most of the models, the answer was surprisingly no. The study found that generally the coherence of the business report didn't significantly decrease, even at high instruction density. Most reports stayed readable, maybe with just a slight dip in quality.
So they could still write okay, even while failing instructions.
For the most part. But there were outliers again, O3 and O4 Mini, those reasoning models. Their report coherence dropped noticeably, to the point where the reports sometimes weren't even considered plausible business reports anymore.
Why them specifically?
The researchers think it might be linked to how many words they output. These models tended to generate shorter reports. At 500 instructions, O3 was only outputting about 1,500 tokens. Think about it, nearly every third word has to be a specific keyword. It's incredibly hard to make the text flow naturally or sound coherent.
Right, it becomes forced. Keyword stuffing.
Exactly. Although, interestingly, Grok 3 managed to keep high coherence even with similar low token counts. So it's not impossible, just harder for some models.
Okay, so pulling this all together, we have these different failure patterns, issues with variance, primacy effects, the shift to omission errors. What's the big picture takeaway?
Well, I think identifying those distinct degradation patterns, threshold, linear, exponential, that gives us a practical framework. You can sort of pick a model based on the pattern that best suits your application. Need near-perfect recall for maybe 100 instructions, go for a threshold degrader. Need predictability over a wide range, maybe linear. Low instruction count. Exponential might be fine and faster.
Tailoring the model choice to the task's instruction load.
Right, and that universal peak in primacy affects around the mid-range density. That's really suggestive. It might point to a deeper architectural limit in how these models handle sequences under load, not just specific model tuning. Plus, the fact that primacy effects fade at extreme loads tells us that our usual prompt engineering tricks might stop working when the model is truly overloaded.
It really drives home that we need to understand more than just the average accuracy. The variance, the way they fail, that's critical for building reliable systems, especially if they're mission critical.
Couldn't agree more. This deep dive shows these systematic shifts in errors, from trying modifications to just giving up and omitting under cognitive load, and it raises real questions about whether focusing too hard on instruction following could actually hurt the quality of the main task for certain models. There are complex trade-offs here.
So This whole exploration using IFScale, it really paints a picture of incredible power, but also clear limits when LLMs face these high cognitive loads. It shows that while they're amazing tools, their ability to juggle lots and lots of simultaneous rules isn't infinite. And importantly, it degrades in these fairly predictable ways. This study really shines a light on the inherent capacities, but also the fundamental limitations of our current LLMs when we push them hard. And it leaves you wondering, doesn't it? What does this systematic degradation, particularly that shift from trying to follow rules selectively to just failing uniformly, what does that really tell us about the nature of cognitive load in these artificial systems? And what does that mean for where we go next in AI development? Lots to think about there. Until next time, keep exploring, keep questioning, and keep deep diving with us into the insights shaping our world.